Great job so far. Now, let's push our analysis a few steps further. What follows is writing the formula for expected portfolio return. It is given by the sum of the weighted annualized average log returns. Wow, this sounded too complicated, but mathematically, it is simple. Just don't overlook this was not the built-in sum function. NumPy has an analogical method that enables summation of values in multidimensional objects, which works perfectly for our situation. So the correct syntax starts by numpy.sum. Okay. The two cells that follow are a refresher. This is the code that will provide the expected portfolio variance and volatility, respectively. Fine. We went through these three cells because we will need the formulas for the return and the volatility in the simulation of the portfolio's mean variance combinations. Yes, that's right. We will create a graph where 1,000 mean variance simulations will be plotted. Therefore, remember the following note, as it is very important. We are not considering 1,000 different investments composed of different stocks. No, we don't do that. We are considering 1,000 combinations of the same two assets, P&G and S&P 500. This means we simulate 1,000 combinations of their weight values. Out of the 1,000 combinations, we will probably have a portfolio composed of 1% P&G and 99% S&P 500, and a portfolio composed of 99% P&G and 1% S&P 500. The idea is to compare the two and see which one is efficient. Okay. In the next cell, the focus is not so much on the code. Try to grasp the reasoning that explains the flow of the related operations. We said our goal is to create a graph that visualizes the hypothetical portfolio returns versus volatilities. Therefore, we will need two objects where we can store this data. So, portfolio returns starts as an empty list we intend to fill with randomly generated expected returns. We apply the same instruction for the portfolio volatilities. Fine. We will need a loop that will be repeated 1,000 times. Here, you see how useful the range function can be, right? In the loop body, we will randomly generate two weights whose sum equals 1. We need two weights because, as we already mentioned, the portfolios comprise two assets. Should its components be over 2, for instance 5, the number of weights generated will be 5. Okay. The next two lines of code are of paramount importance. The key is the append method that will add each newly generated portfolio return value to the list portfolio returns. And this operation will be repeated for each pass of the loop until the portfolio returns list accumulates 1,000 observations. Since we are calculating expected future portfolio return, in the parentheses, we had to insert the formula we mentioned a few minutes ago. On the next line, we repeat the same procedure for portfolio volatilities. We will use the append method and apply the formula for standard deviation. Perfect. Let's see what the portfolio returns and the portfolio volatilities look like. We won't count the number of values, but apparently, these are two super long lists containing 1,000 values each. Anyway, we are on the right track, but we are not quite there yet. First, these lists are hard to manipulate. The third secret we would like to show you is how you can convert these lists into NumPy arrays. We will call these arrays the same names. The syntax is intuitive, and you know it well by now. Just don't skip this important step when plotting the efficient frontier. Right. Now, we can see the two variables have been organized differently this time. They are arrays. Awesome! In the next video, we will plot the results on a graph. Thanks for watching.